Hello, Jeremy here. In this video, we will cover memory and addressing. We'll be focusing on how it is organized and what happens when you address it. And to do so, I will be using my tablet, which is fun. So, yeah, let's start with how memory is usually organized. So, with memory, I'm going to have bytes. One, you address a memory, you usually address a certain number of bits. So this is going to be 8-bit memory, which means I'll be able to address 8 bits at a time. So it will be so there's a byte. I'm keeping them separated for a reason. And this is address 0, 0. So it's address 0, 0. The next byte is going to be address 0, 1, 1, 0, and 1, 1. 0, 1, 2, 3. All right, and then we're going to have there's some more bytes. One, zero, 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 one, zero. Okay, so this is typically how memory is organized. You have the 8 bits or however many bits your memory size is. So naturally the memory size is the size of the register in the CPU, and this is based off of if it's an 8-bit CPU, 16-bit CPU, 32-bit CPU, 64-bit CPU. That typically tells you the register size, and also the bus size, the address bus size, and the data bus size are all typically defined by the bit of the CPU. So here we're dealing with an 8-bit CPU. So I'm just making this up right now. This CPU that we're dealing with is a basic CPU. It has 8 bits for its data and 2 bits for its addressing. So it can address 4 bytes of memory, 8 bits at a time. So this processor has 8-bit registers, and it has 4 8-bit registers. However, we're talking about RAM right now, so this is RAM, and this is a RAM that has 4 bytes of memory. Let's just write this down. So 1 byte, 1 byte equals 8 bits. And there is a reason why I have grouped these together, and I'll take a little sidebar for that. So let me make another layer. Make a copy of that. Activate it. So when we do hexadecimal is a system where it has 16 states that we represent with a single digit. So the idea is this. We can use 4 bits, and that corresponds to a single character in hexadecimal. So 4 binary bits, 4 bits is 1 digit in hexadecimal. So this is why we separate it into 4s. 1, 0, 0, 1, 1, 0, 1, 0, 0, 1. This is 2. This is 3. This is 4. This is 5. And we are at 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1. I'll have to continue this on the next screen, but so this is 6. We know we're going in sequence, but this is a 2, this is a 4, 4 plus 2 is 6, plus 1 is 7, this is the 8 bit, 1, 2, 4, 8, this is 8, plus 1 is 8, plus 1 is 9, 8 plus 2 is 10. All right, plus 10 plus 1 is 11. Okay, so this is where, actually, we need to go back. So we need a digit. 10 doesn't work. We need a new digit. So what happens with hexadecimal, you go with A. 11 is B. And then we continue along with the pattern. I was hoping to do this smaller, but whatever. So we were at 12. 12 is 1, 0, 1, 0. No, that's 10. That's not 12. It's 1, 1, 0, 0, 12. That's the 4th place and the 8th place. So this is C. 1, 1, 0, 1 is D. 1, 1, 1, 0 is E. 1, 1, 1, 1 is F. So this is why hexadecimal notation is convenient when dealing with binary. We can represent 4 bits with 1 digit. Now if we go back to what I was talking about before here, we can represent this memory as hexadecimal. So this is 12, so we know that's a C, and this is 6. 4 and 2 is 6. So this is 6. I have to get rid of that layer that I need. I'll get rid of it real quick. All right, so we have 6C. This is 8, 4, 2. So 14, which is E. This is 8 and 2, which is 10, it's A. We have F0. 1 and 8 and 1 is 9, so 1. So this is how we will do. I just wanted to show how this works. All right. So when we address a memory slot, the CPU says, I want to use address 0, so it'll do that. And then on the data bus will be written this data to the data bus. So we'll have 0, 1, 1, 0, 1, 1, 0, 0, or it can be represented as 6C, and that goes to the data bus. and we want to access another point of memory, like maybe address 2 here, 10, well, we'll get F0. The address 3 will get 19. So this is typically how memory works and how we can represent it in binary or hexadecimal. The reason why this is important is computers typically don't have enough space to hold everything in the processor at once. All right, so if we go and we look at the processor, and you go, like, you can say, okay, here's the processor. Or the CPU. I'll interchangeably use CPU and processor because it's kind of interchangeable. And we have 4 slots for things A, B, C, D. So those are the registers. Now the registers can only hold a byte in this imaginary CPU. So let's say FF 01, C0, and this has 0 in it. So this CPU, this imaginary CPU, can only hold 4 bytes of data, but it can address another, well, it can address the RAM, which can be drawn like this if you want. Yeah, it's kind of bad. And let's say it had 60, sure. 0, 4, 0, 0. This is a 0. All right. This is address 0, address 1, address 2, address 3, which you can also represent in binary. All right. So what the CPU can do is, usually this memory is way bigger. It's way, way, way bigger than the CPU's memory. This is usually thousands, tens of, it's usually a lot bigger than the memory in the CPU, especially these registers. So what happens is if you are dealing with lots of data, let's say you had rows in a spreadsheet and they were numbers. All right, yeah, here we go. Let's do this as an example. Let's pretend these were rows in a spreadsheet and you had a lot of them. What you would do is you would go to the CPU and you would clear out your accumulator. So go ahead and do that. Let's clear out the accumulator. A typically is the accumulator. And you clear it out to 0. This is where we're going to sum up things. This is going to be where we're storing the sum. So we need to start it out at 0. 0 here. And D here is going to be the index or the address we're going to use to address the memory. So what you can say is you can have the computer do an instruction in assembly language. It's move into a register. So we'll say move into register B. What is at the address of B? This is a assembly language instruction. What this means is D, we're going to treat as an address, and I want you to look up the value, this is what these brackets mean, at the address of D. So the address of D is 0. It goes, looks at the RAM, so it puts out an address of 0 on the address bus, and then reads in from RAM and goes, okay, that is a 1, and I'm going to store that value into B. B is already a 1, so it doesn't really change anything. However, it will change what's going to happen. Then what you say is you say add B to A, and that will be our addition operation. It looks similar to what's down here. I guess I can write it. Add A, comma B. So this is add B to A. It's always like that. It's always, this is the destination, this is the source. So this is A equals A plus B. That's how this is read. So we're going to add 1 to this. And get a 1. Okay, and then the next thing we do is we increment the address, which is D, by 1. So now D becomes 1, and we repeat, then we loop back. So look at what's in D. D is now the address of 1. Okay, go look up in memory. What's that address of 1? That's 60. It's stored in D. And 60 becomes 60. And we add this to A. A is now 61. I'm going to change the last number in here because it'll be boring just to add 0 to our value. Let's make this 2, 2. Okay, so we added 61. We now need to increment our address to 2. Now we go back to the beginning of the loop. We look up what at address 2, so address 2 is 4. Move that into B. So this now becomes a 4. I need to do this better. Whatever. Go to 4. And then we add this to A. So now that becomes a 5. And then we increment this with a 3. We look up address 3, which is 22. We store it into B. Becomes 22. And this gets added to A, which is 87. Or 87 hex. It's not quite appropriate to say 87 like it's a decimal number. It's 87 hex. Okay, so this is an example of how addressing and memory and pointers into memory work to add together a bunch of numbers. And as you can see, this is a sequence. If we had more numbers in these memory locations, we could keep doing this. This is what computers are really good at, and you can notice that this is a loop, really low level loop. And I kind of just snuck in some assembly language into here. Oh, how nice. So this is memory, this is how it works, this is how it operates, and this is why I think lots of things start at 0 when dealing with computers. So next video we'll take this idea of addressing and pointers and this memory addressing and start to apply it to Python to start explaining some things that can be mysterious when you first start dealing with it, but it has to do with memory addressing and references and addresses. So thanks for watching. Have a good day.